So we'll continue and we will see the algorithm and find its time complexity for dynamic programming algorithm for matrix chain multiplication. So first we write the algorithm for matrix chain multiplication and then we will find its time complexity. So we take the same algorithm as written in the textbook. Corman, Lizerson, Rivest, Einstein, Introduction to Algorithms. So we have this algorithm, matrix chain order. And here the inputs are, so inputs are the dimensions in the order P0 up to Pn, P0, P1 up to Pn. So we start with two tables, M and S. M stores the optimal cost of evaluating the subproblem from I to J, and Sij, it stores the split point where we split the product. So first we start with the two tables. So let M is n cross n matrix, index from 1 to n, and first dimension 1 to n and second also 1 to n, and S is slightly different. First dimension ranges from 1 to n minus 1, second dimension ranges from 2 to n. So these are, let these be new tables. In dynamic programming, we fill up the table in bottom up manner. So these are the two tables that we will fill. Next we have a for loop for solving the smallest subproblem, which is trivial, for I equal to 1 to n. So the optimal cost for a single matrix is 0 because nothing has to be done. No multiplication is required. The problem is trivial. So we set M Ij is 0. Then, so this is the smallest possible subproblem. Next we solve this is subproblem of size 1. Next we look into subproblems of size 2 going up to n in this order, starting from the smallest going to the largest size wise. So next we have again a for loop for L is equal to 2 to n. So here L is the chain length. So we write here the comment, L is the chain length, which is the subproblem size. So next we have inner for loop. We compute the values of I and j because length L is fixed. So given I, j is uniquely determined using L. So next we have for loop, inner for loop for I equal to 1 to 1 2, it will go to up to n minus l plus 1. So this is the last point up to which I can go, starting from 1 up to this, because length is L. So the end point will be n, the j. So next 6, this we compute the value of j as I plus L minus 1. So j minus I we can compute. J minus I is L minus 1. So that the length from I to j is L. So for initialization purpose, for finding the minimum, we can set initialize ij with some large value like infinity. Then again we have a for loop. So now I and j are determined and length, subproblem length is L. So now we follow the recurrence. So for all possible values of k, now we have a for loop for possible k's. So k can have possibilities. K can start from I, it can go up to j minus 1. Now we find the cost if we split at the point k. So the cost we denote by q. And so q is first cost from I to k. So we have, it is already computed because it is a smaller subproblem, I to k plus remaining cost from k plus 1 to j plus the remaining the cost of multiplying the two matrices. So once again we remember the dimension of the matrices. So for this, the subproblem dimensions are pi minus 1, pi, this goes up to pk. For this, the dimensions are starting from pk, pk plus 1, going up to pj. So if we multiply all these matrices, we get a matrix of dimensions pi minus 1 cross pk, and if we multiply all these matrices, we get matrix of dimension pk cross pj. So finally, when these two matrices are multiplied, the total cost will be pi minus 1 pk pj. So plus, we write here pi minus 1 pk pj. So this is the cost. Now we check this for, we update the minimum, we check this for minimum if we are getting any less. So if q is less than m, so the current minimum is stored in mij, initialized to infinity. So if q is less than mij, we update the values. So we set the new value of mij q, and also we should update the split point. Ij means it is splitting at k. So this is triple for loop. When it finishes, we have computed all the values and we finally return. return m and s. So from this m, if the optimal cost will be m, this 1n, so this will be the optimal cost. So now, given this optimal cost, given these two tables m and s, we can easily recover the optimal parenthesis, and it is also very simple for optimal parenthesization, a very simple recursive algorithm of linear time complexity. So we'll find this time complexity, it will be cubic. So first we find the time complexity, then we'll write the algorithm for computing the optimal parenthesis. So here we are computing only the cost, and show that once given m and s, we can also recover in linear time. So net time for computing both cost as well as the actual parenthesis, it will be cubic time. So now we find the time complexity. So once again we see this algorithm. So this so initially we are initializing this table, and then we have this for loop. So for loop runs for only n times, having constant operations. So the only dominating portion of the algorithm is the triple for loop that dominates. Rest are just constant. Here also it is constant, and for loop goes only up to n, but here we have 3 levels of for loop. So we'll focus on only this triple for loop to find our complexity in asymptotic notation. So the innermost for loop we consider of line starting from line 8 going up to 12. So what operations it is doing? Just constant number of operations from lines 9, 10, 11 and 12. So constant number of operations. So this loop runs for, just take the difference, this take the difference. So we write for loop of line 8 runs for, just take the difference and add 1, j minus 1 minus I plus 1, j minus, this is j minus 1 minus I, j minus 1 minus I plus 1, this is j minus I, these many times. And for each iteration, the operations are only constant in number. So we can say that here the time complexity is, using big theta notation, this is L minus 1, because our L is, if we see from this equation, value of L is j minus I plus 1, or well, better we can see value of L minus 1 is j minus I. So this j minus I is actually L minus 1. So big theta of L minus 1 is the complexity of the for loop at line 8. Next we consider for loop of line 5. So this runs for n minus L plus 1 times. So we multiply it, n minus L plus 1. So for loop of line 5. So just multiply this by n minus L plus 1. n minus l plus 1. So it has the time complexity big theta of n minus l plus 1, l minus 1. Now we consider for loop of line 4. So this runs from l equal to 2 to n. So just we make the summation. So the time complexity we can write as a summation from l equal to 2 to n. So we can write this Tn is equal to, call it T2n. This is summation of all l is equal to 2 to n big theta of n minus l plus 1, l minus 1. So next what we do is, for simplification, call this L prime, make a substitution, call this L prime. So this is actually n minus L prime. So this will simplify our expressions. So as L goes from 2 to n, L prime goes from 1 to n minus 1. So using this change of variable, we can write this as, and also we can take this theta, big theta out and write sum of L prime is 1 to n minus 1, n minus L prime, L prime. So this will simplify our computation. Now once again we further simplify this big theta of, so we break this in two parts, n times L prime minus L square. So we write this as n times sum of L, n is constant here, L prime is only L prime is varying, L prime is 1 from n to n minus 1, L prime minus sum of L prime is equal to 1 to n minus 1, L prime square. So now we write the formula of summation, sum of n natural numbers and sum of square of natural numbers. So this, using the formula big theta of n times n minus 1 n by 2 minus n minus 1 n to n minus 1 divided by 6 big theta of. So we simplify this expression and get here n cube minus n square divided by 2 minus. So here we simplify. So this we multiply by 3 and we get 2n cube. So 2n cube we get. Then for second term we multiply these, we get minus 2 here we get, and minus 1 minus 3 minus 3n square, and minus 1 is 1, we get plus n 6. So now there is no need to make exact calculation, only thing observe that this cubic term survives. N cube by 2 minus n cube by 3, n cube by 6 we get. So lower terms we can ignore, constant factors also we can ignore. So big theta of n cube we get. So our dynamic programming algorithm is big theta of n cube, a polynomial time algorithm. Just compare it with brute force algorithm having time complexity big omega of 4 to the power n divided by square root of n. So there is a big difference in time complexity if we apply dynamic programming as compared to brute force algorithm. So once we are given the tables M and S, we can recover in linear time. So net complexity will be this much plus linear time, again n cube, for actual parenthesization. And the algorithm is very simple, a very simple recursive algorithm. Simply use this S array to find the breakpoint, split point k, and then again recursively apply the same procedure again and again. So algorithm is very simple. I will write the algorithm and find its time complexity. So for actual parenthesization, we have print optimal parenthesis. Print optimal parenthesis. So with just this split array, we can find. So first, the basis of this recursion. If we have single subproblem, then nothing has to be done. Just print the matrix in parenthesis. Print AI in parenthesis. Else otherwise we print opening parenthesis, then apply recursion. Print first half of the problem, complete parenthesis. Print optimal, we call this the same algorithm, parenthesis, and the parameters passed are S matrix, initial point, and the split point. Split point is given by Sij. After this, we print the second half. Similarly, using recursion, print optimal, parenthesis, parameters passed are S, split point plus 1, split point is Sij plus 1 and j. Once this is done, we close the parenthesis. So this is the algorithm, and for this, so initially what we do is, for original problem we use these values, set I equal to 1 and set j equal to n. Call this recursive algorithm and we'll find the optimal parenthesis. So for time complexity, suppose we denote this time complexity by Tn. So Tn is 1 if n is 1, otherwise it is equal to, if we consider the split point, call it k, it is splitting at k. So first half of the problem, it will have length k, second half will have length n minus k. Here for this we can take as a constant c. So now we can easily solve this. So it depends on how this k splits. If it splits like exactly in between, so it will be like binary search, and it best case complexity will be log of n with base 2, like this. This breaks into half again, and so on. So but we are interested in finding worst case time complexity. So worst case time complexity is when it splits, one of them have size smallest possible one, other the largest possible. So in that case we'll get like this something like this. This is equal to, the worst case scenario is this, t1 plus t n minus 1 and so on. This will repeat, t1 plus t1 plus t n minus 2 and so on. So we can easily see this will continue up to n t1. This will go up to t1 1 2 so yes, n minus 1, yes, this will be n t1, so cn we get. So now the time complexity is big O of n. So in linear time we can recover given the matrix S. Now we'll take a very simple example and see how we can make the table, how we compute the table, and finally how we compute the optimal cost and also optimal parenthesis. So the example problem we take this example. So the matrices are: A is 6 cross 7, B is 7 cross 3, C is 3 cross 1, D is 1 cross 2, E is 2 cross 4, F is 4 cross 5. So we can see that dimensions are in proper order. Now we'll make the tables for M and S. So the tables we make first for M. So it will be something like a, we can say like pyramid structure or triangular structure. We'll see why this is required. Make a triangular structure like this, and we have 6. We have 6 1 2 3 4 5 6 matrices. So we divide in 6 parts like this. 6 parts we divide, like this, and here also we divide in 6 parts. This. One, two, three, 4, 5, 6. So we label, on left we have J, this is matrix M, table M. At the right we have is index I, and how they vary. J is from 1 to 6, 1 2 3 4 5 6. I is from 1 to 6 top to bottom, 1 2 3 4 5 6. Similar way we make S table. S table will have 5 entries. Make S table having 5 entries. So we can divide like this: 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. Now we make this is S table. Here also we label similar way but slightly different. So it will range from 2 to 6. 2, 3, 4, 5, 6, and here 1 to 5. 1, 2, 3, 4, 5. This is because for same I and j there is no need to split, no need to store the values. So we start with the smallest subproblem. Smallest subproblem is M11 of single size. So if we consider this way, these are the smallest subproblem of size 1. So we can see 1 1, this is 2 2, this is 3 3, this is 4 4, this is 5 5, and this is 6 6. So these are the smallest subproblem having a single matrix, and for a single matrix cost is 0. So we start with values all zeros. So next we have this next level of size 2. So we can see 1 2, this is 2 3, 3 4, this is 4 5, and this is 5 6. So problems of size 2. So here we compute. So for a problem of size 2, we have to multiply 2 matrices. So for reference we will write these, we can see here. So this problem is 1 2. 1 2 means this A and B. So the cost is 6 multiplied by 7 multiplied by 3. So we get 126. 6 7 3, 126 we get. So this way we fill the table 126. Next we have 2 to 3 subproblem. 2 to 3 subproblem. 7 3 1 is the cost, 21. We write here 21. Next we have 3 to 4 cost. 3 to 4 means CD. 312. 312 is 6. We get the cost 6. Next we have 4 to 5. 4 to 5. 1 2 3. 4 to 5 is DE. Cost is 1 2 4 is 8. Next is 5 6. 5 6 2 4 5 is 40. So for we also fill the split table. So now it is trivial. 1 2 it will split at point 1. So 1 2 entry is 1. 1 2 entry is 1. Similarly other entries we fill. 2 3 entry, it will split at point 2. 3 4 splits at 3. 4 5 splits at 4. 5 6 splits at 5. So these are initial values. Next, at this level you can see these are subproblems of size 3. 1 1 to 3. This 1 3. This is 2 to 4. 3 to 5. 4 to 6. So now how we fill it? So here there is a very simple pattern, and we simply follow the pattern. So we have to look for the smaller subproblems. Smaller subproblems in the table. Take for example this value. This is M13. So M13 can split at, there are two possibilities. It can split at 1 or 2. So for M13, this M13, it can split at 1. If it splits at 1, then we will have M11, M11. This is M11 and M12. M1 no, not M11, and then remaining problem is 2 to 3, M23. So just see where is M23. This is M23, this 26, not 21. So this is M23, this, and M11, this. So here we'll see a pattern like this. If we consider this row and columns, so starting with the lowest here and starting with the highest, so range is from this just below it. So this is the combination, take this and this and take this and this. So this and this, M11 and M23. So 0 plus 21, 0 plus 21. So we write here M13. We have to see 0 plus 21. M13 is equal to minimum of, I will just write the values. First combination was 0, 0 and 21. 0 plus 21 plus cost. We'll evaluate it again. Then second possibility is 126 plus 0. 126 plus 0, again plus cost. So now the cost is for the multiplying the two matrices. So this 1 1 matrix, the result of this 1 1 matrix, and this 2 3 matrix. So we have to see here, this is 1 1 matrix and 2 3 matrix, its result. So the result of 2 3 matrix will be 7 7 1 7 1 and 6 7 1. So 6 7 1. So a simple rule we can follow. The split point we are getting 6 7, the k where we are splitting 6 7, and the last dimension 6 7 1. 6 7 1, 6 7 1. Same way here. Now the split point is, for the second problem, this is the split point. So once again we get 7 3 1, 7 3 1, 7 3 1. We have to find minimum. So there is no need to find exact values when we surely know that this is the minimum. We get 42 plus 21 is 63. So we write the value 63 in the cost. And also store the split value. Split value is 1. So here we write the value 1. Same way we continue for others also. Here this is M24. So M24 we write is equal to minimum. Same pattern will follow. Here first combination is this, second combination is this. No. First combination is this, second combination is this. So first is 0 6, second is 21 0. 0 6 21 0, 0 6 0 6 21 0, and plus cost. So just consider the split point. The problem is 2 to 4, 2 to 4, splitting at 2, 2 to 4 splitting at 2. 2 to 4, 2 3 4. Here we split, so we get 7 3 and 2, 7 3 2, 7 3 2. Same way for the second split point. We consider here this 2 3 and 4. These two multiply and we get 7 3 7 7 1, 7 1 matrix, and this 2 7 1 2, 7 1 2, 7 1 2. So now we can compute. So 7 3 7 6 is 42. This will be 42 plus 6, and this will be 21 plus 14, 35. This will be 48. So we get this value 35. We get 35. We write the value 35 here, and split point is this. We are taking this and this, so the split point is 2 3, not 2 1 2, 2 3 3. Split point is 3, so we write here 3. Next we consider this value, M35. M35 we write M35 is equal to, again, what are the possibilities? So first we have 08 second is 60, 08 and 60, 08 and 60 plus the cost for 3 to 5. 08 means we are splitting at 3. The problem is 3 to 5, 3 4 5, C to E, and we are breaking at 3. So the first matrix is 3 1, second is 1 4, 3 1, 3 1 and 1 4. We get 3 1 4, 3 1 4. Second possibility is 60 possibility. So we are breaking at this 3 4 5 5, 3 4 and 5, 1 2 3, 3 4, and this is 5. So 3 4 we get 3 2, 3 2, 3 2 with 2 4, 3 2 4, 3 2 4 we get. We compute this as 8 plus 12 is 20. This we compute as 6 plus 8 3 is 24 is 30. So 20 we get 20, and so we write the value 20, and the split point is this combination. So 3 3, we are splitting at 3. We are splitting at 3, so we write the value 3 here. Next we consider this 4 6 value, M46. M46 is equal to minimum. The two possibilities are is 4 6 0 0 40 80. 0 40 8 0 0 40 8 0, and the cost 0 40 means it is splitting at 4, splitting at 4, 1 2 3 4. Splitting at 4 means we have first matrix 1 2, second this product matrix of dimension 2 5, 2 5 1 2 2 5 1 2 5 1 2 5. Second possibility 8 0 possibility. Here we are 8 and 0. So now we are splitting at 5, splitting at 5, splitting at 5 1 2 3 4 5. Here we are splitting. So this product is 1 2 4 is 1 4 1 4 and 4 5 1 4 5 1 4 5 1 4 5. So obviously this is large, this is small. We compute this as 28. Write the value 28. This is second possibility. Value is 28, and split point is the second combination. Second combination 8 0 8 0 8 0 means 4 5. We are splitting at 5. We are splitting at 5. Just write the value 5 here. So now we have completed sub problems of length 3. Now we consider sub problems of length 4. So these are 1 to 4, 2 to 5 and 3 to 6. So first we start with 1 to 4. M1 to 4. Now we'll have 3 possibilities for minimum. We write all possibilities. This is 1 to 4. Now the 3 possibilities are, consider this and this, and one possibility, first possibility is 0 35, second is 126 6, third is 63 0. So we write one by one. 0 35, 0 35, second possibility is 0 35 126 6, 126 6, third possibility is 63 and 0, 63 and 0, 63 and 0. Now the cost we have to consider 1 to 4. In the 1 to 4 problem, this combination we are splitting at 1. 1 2 3 4. Here we are splitting. So first matrix is 6 7, second 1 2 3 4. This combined matrix multiplication dimension we get is 7 2, 7 2, 6 7 7 2 6 7 2, 6 7 2, 6 7 2. Second combination we see, second combination we split at point 2, split at point 2. First matrix dimension is 6 3, second is 3 2, 6 3 3 2 6 3 2, 6 3 2. Third possibility is we split at 3.3. The matrix is first matrix is 6 1, second is 1 2, 6 1 1 2 6 1 2, 6 1 2. Now we minimize. So this is 12 and 63, we get 75, and this here we get 42, 84. So 75 is the minimum, so we get this as 75. And this is third possibility, 75, we write 75, and the split point is third possibility. This is the third possibility. We split at 0.3. We split at 0.3. So here we write the value 3. Same way we continue. Next we have 2 to 5 value. M25. We consider the possibilities. So now the possibilities are 0, 20, 21, 8, 35, 0. 0, 20, 0, 20, second is 21, 8, 0, 20, 21, 8, 21, 8 and 35, 0. 21, 8, 21, 8, 35, 0. Now we see the cost. So the costs are first possibility 0 to 20, we split at 0.2 from 2 to 5. 2 to 5, 2, 3, 4, 5. We split at 0.2. First matrix is 7, 3. Second matrix is 3, 4. 7, 3, 3, 4, 7, 3, 4. 7, 3, 4. 7, 3, 4. Second possibility we see 21, 8. This 21, 8, it splits at 3, 3, 2, 3, 4, 5. So first half is 7, 1. Second half is 1, 4. 7, 1, 1, 4, 7, 1, 4. 7, 1, 4. 7, 1, 4. Third possibility. Third possibility, it splits at 0.35. So this is 2, 4, 4. 2, 3, 4. 1, 2, 2, 3, 4. So dimension we get is 7, 2. 7, 2. 7, 2, 2, 4. 7, 2, 4. 7, 2, 4. And we minimize this. So this time we get we compute the values. This is 84, and here we get 28, 28, 36, 57. This is the minimum. So there is no need to compute all if we know which one is the minimum. Here we are getting value 84, and here 35 plus 8, 7, 56. So these are high value, this is low value. So we get this as 57, and this is the split point. So we write the cost 57, 57, and the split point is the second 21, 8 combination. 21, 8 combination. This 21, 8 means it is splitting at 0.3. Splitting at 0.3. 25 is splitting at 0.3. This 25. Just write value 3. Now next value is 3 to 6, m3 to 6. m3 to 6 is equal to minimum of 3 to 6. Now the three possibilities are 0, 28, 640, 20, 0. 0, 28, 0, 28. Second possibility is 0, 28, 640, 640, 20, 0. 640, 640, 20, 0. And the cost 0, 28 combination, 0, 28 splitting point is 3 to 6 problem. 1, 2, 3, 3 to 6 splits at 3. First matrix is 3 1, second matrix is 1 5, 3 1 1 5, 3 1 5. Second combination is 640, 640. Splitting point is 4. This is the splitting point. First matrix is 3 2, second is 2 5, 3 2 2 5, 3 2 5, 3 2 5. Third combination is 20 0. 20 0 splits at 5, 5, 3 4 5. So first matrix is 3 4 and then 4 5, 3 4 5, 3 4 5, 3 4 5. Now we compute the minimum. So this is 43. Here we are getting larger values, here also larger values. So this is the minimum. 43 we get. Splitting point is this first 0 28 combination. Cost is 43. Write the value 43 and splitting point is the first combination 3 splits at 3. Splits at 3.3. So next is sub problems of size 5, 1 5 and 2 6. So first is M15. M15. Now we'll have 4 combinations. 1 5. So there are several combinations like 0 57, 126 20, 63 8, 75 0. First is 0 57. 0 57. Second is 0 57, 126 20. 126 20. Third is 126 20. Third is 63 8. 63 8, 75 0. 63 8, 63 8, 75 0. 63 8, 75 0. And the cost 0 57 combination, 0 57 splitting at point 1. First matrix is 6 7, second is 7 7 4, 6 7 7 4, 6 7 4. 6 7 4. Second combination splits 126 splits at 2. First matrix is 6.3, second is 6.3.3.4, 6.3.4, 6.3.4, 63.8, 63.8 splits at 0.3. First matrix is 6.1, 6.1, 1.4, 6.1.4, 6.1.4. Then 75, splitting at 75, splitting at 4, 4. So we get 6.2.2.4, 6.2.4. Now we find the minimum. So here what value we get? So again there is no need to compute. We can easily see that these values are too high. This is the lowest value, this will be the minimum. So I will compute this. 63 plus 8 plus 24, we get the value 95. This is 95, so we get this value as 95. We write the value 95 here, and the splitting point is 1 2 3 63 8 combination, 63 8 combination. So it splits at 3, it splits at 3, so write here 3. Now next we have M26, M26 is equal to minimum of, again we will have 4 possibilities. And the possibilities are this starting from 0.43, 0.43, first combination 0.43 plus second combination is 0.43, 126, 28, 126, 28, 126, 28. Third is 126, 28. Third is 63.40, 6. First was 0.43, 126, 28, 126, 28. Third will be 63.40, 63.40. No, not 0.43 first, second will be 21. So it was my mistake, I will correct it. So first is 0.43, second will be 21, 28, 21, 28 is second, 21, 28, 21, 28, 21, 28. Third will be this 21, 28, 35, 40, 35, 40, 35, 40, and fourth will be 57, 0, 57, 0, 57, 0, and the cost. So 0.43 combination, this 0.43 combination we are splitting at 0.2, 0.2. So we have 7.3 and 3.5, 7.35, 7.35, 7.35, 21, 28 combination. We are splitting at 0.3. This is 0.3. So we have 7 1 7 1 1 5 7 1 5 7 1 5 7 1 5 35 40 combination. 35 splitting at 4 2 3 4 2 3 4. So dimension is 7 2 7 2 and 2 5 7 2 5 7 2 5 57 0 combination. 57 splitting at 5. Here dimension is 7 4 4 5 7 4 5 7 4 5. Now we find the minimum. So here we can estimate 15. These are large values. 70, more than 100 we will get. This seems to be the minimum, and we compute this as 21 plus 28 plus 7 5 35 84 we get 84. So just write this as 84, and it splits at combination 21 a 28. Write the value 84. 84 here. Splitting point is this combination 21 28 21 28 21 splits at, again splits at 3, splits at 3. So now we have the original problem M16. We'll have 5 sub problems. We write it as before. M16 is equal to minimum of all possible combinations. We write there are 5 possibilities. So we have the possibility 0 84 126 43 63 28 75 40 95 0. So one by one we write. First is 0 84 0 84. Second is 126 43 126 43 126 43. Third is 63 28 63 28 63 28. Next is 63 28. Next is 75 40 75 40 95 0 75 40 75 40 95 0. Now we consider the cost. So now we have seen the pattern, very simple. This one will split at point 1 2 3 4 5 like this. So we can directly write the product of the dimensions. So first splits at point 1. This 0 84 combination splits at 1. So 6 7, then 7 5 6 7 5 6 7 5. Second combination 126 splits at point 2. Point 2 first is 6 3 6 3 3 5 6 3 5 6 3 5 6 3 5. Next we have 63 combination split set 0.3, 0.3, 6115, 615. 615, 75, split set 4, this is 0.4, 6225, 625. And last cost 95, split set 5. So first is 6445, 645. Again, there is no need to compute all values. We can see these are high values. This will be the minimum. And so we compute the optimal cost. 63 plus 28 plus 65 is 30. We get 121. So this we get 121. Splitting point is 6328 combination. 121 we write. Split set combination third 638. 638 split set 0.3. So here we write 3. So now we have, through a very lengthy computation, we have computed our S and M tables. So this is the optimal cost. 121 scalar multiplication we have to do. How to get optimal parenthesis? So initially we have to split at 0.3. So now we can write the product of 6 matrices. Just apply the recursive algorithm. A, so I am not writing the dimension for just for simplicity. A, B, C, D, E, F. This is the original problem. Split at 0.3. So take the bracket. First sub problem is A, B, C. Second sub problem is D, E, F. So here this is 1 and this is 6. So this K we get is by consulting S16. We got 3. So next here we have 1, this is 3, this is 4, and this is 6. So next we have to consult S13 for here splitting ABC. For splitting DEF we require S46. So we consult the table S13 and S46. So what is S13? S13, S13. So S13 value is 1. This is equal to 1. So 1 means we have to split like this. Now next is S46 value. S46 value. So S46 value is 5. S46 is 5. This is equal to 5. 5 means we have to split like this. So next level we'll write this is equal to continuing so here also first we apply the brackets and split at point A, B, C. Then here also take the bracket for second sub problem. First sub problem is DE and split at F. Apply the bracket. So here we have one. So these are trivial splits. We can consult the table, but we can also directly write these are consecutive values of I and j. So consecutive value means it's a problem of size 2 and it trivially splits in half. So either way we can write directly. So BC, it has to split in BC. So write this as A, BC, DE, F. So this is the complete parenthesization, and here what we are doing is like first multiply B and C, get the result, multiply by A, multiply D and E, get the result, multiply by F. Now multiply the two results to get back the original result. This is the optimal parenthesization, and the optimal cost is 121.